So if you've watched my last two videos, you know how to create the vector equation of a line in 3D space. Hopefully, you're now a bit curious about what else you can do with these lines. So one thing we like to know about lines is, do they cross one another? And if they do, where does that occur? So looking at the black and the blue lines that I've drawn on the screen here, it appears like these two lines cross each other. Now this is like looking down on a problem. So if you were above a situation and looking down on it, we could have, say, the path of two aeroplanes modelled by those two lines there. The issue is we're in three-dimensional space, so we do actually need to consider what's happening in the third dimension. Now, in reality, it's quite possible that these two lines are actually doing something like this in three-dimensional space, and the point that we can see as an intersecting point there is actually just the point where they are above the same space on the ground, say, so on our x and y. But there's a vast difference between their z values. So those two lines aren't intersecting. When we are looking at lines in 3D space, we must be convinced that they cross in all three dimensions. It's tempting to think that once you've found an intersecting value in 2 dimensions that you're done, but actually we do need to be convinced that we cross over in all 3 dimensions. Hopefully that's fairly intuitively obvious to you, but it's the sort of thing that you might forget to do in the exam as you're sort of rushing through your paper. So let's look at these two lines here. I've got L1 and L2. Now don't forget they've notated with this left hand side R, which is meant to represent any point you like on the line. Your y equals mx plus c, your y bit, that kind of y coordinate. It's not quite the same here, but it is this general point on the line. Now, if these two lines are to meet one another, that value of r that we are selecting, our point on the line that we're interested in, will be the same. If they're intersecting, they will cross at a single point we should be able to find. So I can make these two equations equal each other by using the fact that r would be the same. Hopefully, again, that's fairly intuitive to you as a concept. So that has given me now an equation which doesn't look that nice to pull apart, but of course we know that we can consider the i's, the x's, the j's and the k's individually as sort of separate components. So if I look at the I components, the top rows of all of my vectors there, I've got minus 8 plus 3 mu equals 3 plus lambda. If I look at my j's, I've got minus 3 plus 1 mu equals 8 plus 4 lambda. And if I look at my k's, I've got 0 plus mu equals 3. Well, that's immediately given me something quite nice there. In the k dimension, or the z dimension, I guess, if we're dealing with a context problem, I have been able to find out that mu is 3. Well, that should now allow me to substitute that value back into one of the other equations and find lambda. So minus 3 plus 3, which is our mu value, equals 8 plus 4 lambda. And solving that equation, we would get that lambda is minus 2. Great. What does that tell me? Well, that tells me that for the value of mu equals 3 and the value of lambda equals minus 2, these two lines meet each other in the j and k dimensions. This is what I mean about checking in that third dimension. So far, all I've done is created that first problem. All I can be sure of is that when you look at the problem from some angle, they appear to cross. I need to be sure that they do actually cross by checking that these two values, this value of lambda and this value of mu, work in this third dimension. Okay, so if we do that then, minus 8 plus 3 lots of mu, which is 3, that would give me minus 8 plus 9, which is 1, is that the same as 3 plus minus 2? It is. Good. Therefore, these two lines intersect. It will probably say show that these two lines intersect, show that equations always have conclusions. Therefore, they intersect, and we should find the point of intersection. So where are they intersecting? Well, we can do that precisely by doing exactly what I've done in blue on the top line there, substituting in our value of mu or our value of lambda, either one, because we know they're landing out on the same point, into the equations and come out with an expression for r, or this particular point I'm interested in this problem. Okay, if I do that, I end up with 1, 0, 3, I believe, and I will just check that in the other equation. 1, 0, 3. Perfect. So what about if they don't intersect? What about the situation where when you created your 3 equations in the 3 dimensions of your line and you solved 2 of them, probably simultaneously, to find values of mu and lambda or whatever your multiples are, and then you went to check that in your 3rd equation, it didn't work. What would happen then? Well, there are 2 options. The first option is what's going to happen with these 2 lines here. Now, the beady-eyed among you might have already spotted something particular about the 2 direction vectors in this problem. Don't forget the direction vectors are these ones here. You might have spotted that these 2 direction vectors are in fact multiples of each other. And we know that multiples of the same direction vector will mean that the 2 lines are parallel. Now, by definition, we know that parallel lines never cross. So if they don't intersect, if that previous technique falls apart when you go to check in the 3rd equation, one option is that your 2 lines are parallel. And you would show that by identifying that the direction vectors are indeed multiples of each other. You'd still have to show it, you'd have to identify that and write some words to explain that to your examiner, but you could do that quite quickly. You don't need to do any further calculations there. If your 3 equation system breaks down, so you've solved your simultaneous equations, you found your values, you plug them into the 3rd equation and you don't get a consistent equation there, and you've checked that your 2 direction vectors are not parallel by checking that they're multiples of each other, the lines in this 3rd scenario will be skew. And skew lines is effectively that problem that we looked at right at the beginning of this video. So where they pass over each other and will never meet. So those are your options then. For vector equations of lines in 3D space, they either intersect at a known point, and you would do that by doing your component equations, solving simultaneous equations and checking in the 3rd dimension, then giving your point of intersection as well. If that doesn't work, you've got 2 options. You're either parallel, and you're looking for a multiple of the direction vector in either case, and you again would explain that using some language to your examiner, and if those 2 conditions fall apart, you must have skew lines.